Hello, and welcome to problem set 121. Today we're going to talk all about series, and so it's going to be a great day. Now, as I hinted to earlier on, we are going to have a bunch of different theorems or equations or formulas for dealing with series. We already talked about our telescoping series. You see that each subsequent term kind of subtracts off something from the previous term and they fit together. And so you can see where those converge or how they converge. We also talked about geometric series. So let's review. So a geometric series, if I want the sum of that, that would be a1 over 1 minus r, whatever the common ratio is. The telescoping series, generally, it's whatever the first term is, but I get a new marker today. Generally, it's whatever the first term is, but that's not always true. Look at this. This is teacher gold right here. 36 individually packaged markers. Yeah. Get rid of that one. Straight into the trash, of course. Next, we are going to talk about the divergence theorem. And you actually, sometimes they take a little time to warm up in the morning. Divergence theorem is simple. You've already done it, and that is this. If the limit as n approaches infinity of your sequence an does not equal 0, let's do it that way, then the series diverges. So that's your divergence theorem. So what are the problems going to look like? Well, you might ask, does this series diverge? Now, be careful. It doesn't mean that if your terms at infinity go to 0, it guarantees that your sequence converges. That's not true. This is simply saying that if it goes to 0, if it does not go to 0, then it diverges. Okay. That's why we did all that stuff with logic at the beginning of the year with the contrapositive. If the limit is 0, then you can't necessarily say that your series converges, right? We only know about things when the series diverges. Okay, so you have to be really, really careful there. The converse is not true. So let's determine whether each of these converge or diverge. This guy, if I take the limit of an as n approaches infinity, that equals infinity. So this definitely diverges because infinity is not 0. Are we surprised? Nope. Let's try this one. Okay, so this, if I take the limit as n approaches infinity of 1 over n, I get 0. Does that mean it converges? No. In fact, we know nothing about this result. If the limit as n approaches infinity is 0, our theorem tells us nothing. So we're going to leave this as a giant question mark for a future lesson when we'll find out that that actually diverges. Next one, let's try this. 2n minus 3 over 3n. So let's take the limit as n approaches infinity of 2n minus 3 over 3n. That's 2/3 by L'Hopital's rule. So this series diverges, which means it won't settle on a nice number. That's okay. Now, moving on, they're going to ask you to do some addition and subtraction things, such as this. Determine whether each of the following series converges or diverges. If a series converges, determine its value. So we have 300 plus 25 plus 1,000. I don't know why they give us like a basic math problem attached to this, like very much not basic math problem, where n equals 1 to infinity. So we can add these up easily, right? It's 1325. What is the value of this? Well, in case I don't see it, I could do the divergence theorem. I'm going to find out that 1 over 2 to the n goes to 0. So that tells me nothing. It could converge, it could diverge. So let's write out the first couple of terms. 1/2 plus 1/4 plus 1/8. This looks like each time I'm multiplying by 1/2, and my original term was 1/2. So I'm going to use the sum of a geometric series, a1 over 1 minus r. So that looks like 1. So this whole thing converges to 1, so the answer is 13/26. I know I jumped through that pretty quickly, but this was a review from a previous lesson. So we learned the divergence theorem, so we'll leave that guy up there. That's pretty cool. Now let's look at some other things. Now this part of our lesson is interesting because until now, you have been stuck with whatever boundaries they've given you. So let's say we had a sum that was n equals 1 to infinity of 2 over 3 to the n. Now that's great and all, but what if you wanted instead to start with n equals 0? Well, let me phrase this to you in this way. We can easily change our bounds, but let me call it a different letter. Let's call it x for a second, and I'll change it back in a second. How would you describe the relationship between x and n? Well, it looks like x equals n minus 1. Or, if I were to solve for n equals x plus 1. So all I'm going to do with my series is I'm going to plug in for n this change formula. Now let's check to make sure we've done this correctly. Our first term would be 2/3. Our next term would be 2/9, 3 squared. Our next term would be 2/27 and 2/81, and so on. Always make sure you do that plus ... because this is a series. It goes on forever to infinity. Now, with this change of index, let's see if it works. If I plug in 0, I get 2 over 0 plus 1, which is 2/3. 2 over 1 plus 1, which is 2/9, 2/27. So they do match up. The last thing that I would say, so you don't look like a novice, is that you should really rewrite this in terms of n. Because we like n, and we really don't like x as an index. I almost wrote x again. So this sequence is identical to that one. I just wanted a changed base. And so they could ask you to change your base. What you're going to do is look at what you want to change the base to, write this equation, and then remember to solve for n so that you know, oh, right, you could errantly plug in x minus or n minus 1 here instead of n plus 1. So it's always important just to do that double check to make sure, and then plug in a couple of terms to make sure you got the same thing out. But sometimes we like to change that, and that's okay. Now, just like limits, just like derivatives, just like integrals, just like functions, way back in Algebra 1, we must do the dreaded sum, difference. I don't think we're doing product. We are doing product. Sum, difference, and product of series. So let's say you have some series, an, that converges. And some other series, bn, that converges. Let's call this A and B. So, what happens if I add these two convergent series? Well, that simply equals A plus B. Okay? Are we surprised? No. If both of these converge and I add them, no problem. What happens if I subtract them? Well, that's A minus B. Are we surprised? Not really. I'm off screen. Here we go. Now, what happens if AN converges, but BN diverges? Well, when we add these two, then that sum will still diverge. Because this is going to converge to some friendly number. This is just going to keep getting bigger and bigger and bigger. And so it will take over. Similarly, if you subtract them, you have one that converges and you have one that diverges. That also diverges. Here's where it gets a little tricky. What if they both diverge? Then the sum definitely diverges. The difference, you really don't know. You can't guarantee that it's 0. So let's write that out here. AN diverges. And actually, since diverges doesn't tell us if it's positive or negative, we don't even know the sum. So there's no quick and fast rule to say this diverges or this converges. Why? Well, because some functions will diverge faster than others. It's just like the limits that we did earlier. Think about this limit. If I take the limit as x approaches infinity of x, and I subtract the limit as x approaches infinity of x squared, which one wins? Well, the x squared is going to win, right? So this is negative infinity. Even though I have a positive infinity, and then I'm subtracting a bigger infinity, which is kind of funky. So, you have to be very, very careful. I know that this feels like you want 0, right? Because it's infinity minus infinity. That's just not true, okay? Infinity, even though it's this random, weird thing that comes out of nowhere, right? And we just use it to describe really big numbers. Unfortunately, infinity is attached to whatever function you use to get to infinity. And so you kind of have to be very careful with those things. So if they both converge, easy peasy. If only one of them diverges, you're set. If both of them diverge, you have no clue what's going on. And we have to look for other tricks there. Finally, if you multiply a series by a constant, you get that constant multiplied by a series. So that, my friends, is problem set 121.